Hello, in this video, we will demonstrate a mock interview of a typical coding interview of a technology company. The central theme of the demonstration is to illustrate how the solution to an algorithmic problem may be constructed systematically. It is vital to come up with a working solution to the problem in the first few minutes of the interview. Note that this initial solution may be a brute force solution and far from optimal. You should be able to clearly articulate your thoughts and write working code for your solution. This conveys to the interviewer that you are capable of thinking computationally. You should also be able to quantify your solution in terms of the time complexity and also the space complexity. The next step in the process is to try to improve upon your initial solution. The time and space complexity often provide valuable clues here. For instance, if your initial solution is of the time complexity big O of n squared, you might be able to bring it down to big O of n log n or even big O of n, perhaps by trading space for the time. You should keep your eyes and ears open for any hints provided by the interviewer during the course of the interview. We will demonstrate some of these points in the following mock interview session. But remember, you need to practice several mock interviews with your friends or mentors to get comfortable with the process. Good luck.
Hi, I'm Narsundata.
Hello, I'm Chinna Mankapur.
Hi Channa, how was your day so far?
It's been going great, thank you.
Okay, so in this interview, I'll be mainly assessing your problem solving abilities. Okay, is it fine? Shall we get started?
Sure.
Okay, so how do you print a single linked list in reverse order?
Alright. Yeah, printing a list obviously requires a linked list. Let me list down the assumptions I have made. So it has a node. A node looks like this. Suppose at minimum it has data which is printable, and it has a reference pointer for the next node. So a single linked list starts with the first node, and then the first node points to the second one, and so on till the last node. And this is a null terminated linked list, and it has n nodes. So if this is node number 1, 2, and some ith node in between, and then the nth node at the end. So this is the linked list I am assuming, and printing this one in the reverse order is essentially printing nth node first, and then the node at offset n minus 1, and so on up to first node. Okay. At the top of my mind, I have a brute force solution, which is to print the list in reverse order. The brute force approach is very simple in this case, where you go seek to the nth node first and then print it, and then seek to the node at n minus 1 offset and print it, and so on up to first node. You seek to the first node and print it. Right? So essentially, we are going to print ith node where I starts from n and then down to 1.
Sounds good. Can you write the C code for this algorithm?
Sure. So this doesn't need to be returned anything, so I'm going to use void as the return type, and I'm going to call this function as print_rev. So node is the type def of struct node, so which has these two fields which are of our interest, and L is that list which is starting with. And so to start with, my approach requires to print ith node where I starts with the nth node and then down to 1. So I need I to be equal to n to start with, and we don't know n actually, sorry. So we need to know the length of the list that is not given. So n is length of the list. So this can be found out in a simple linear method, it's very trivial. So then I is, this is essentially int n, and then we have int I, that is, actually we don't need int I because this is essentially a simple for loop. So I'll start with for loop, int I equals to n to start with, and as long as it is 1 I can go, so as long as it is greater than 0 I keep going there. and every time I decrements. So in one pass of this loop, we are going to seek to the ith node and print it. So I'll call, so basically I need to access a node n, n node. This is going to, we need to seek to ith node here of the list L. And again, this is a trivial linear method to seek to ith node. Right. Once I get to this node, I'm going to print it. So again, this is C code, so I need to know the data type of the data. So I'm going to assume an int here. So in this case, printf %d for printing it in decimal, and node, this is a pointer, so it's going to be like this. So data. So I decrements, and that's all. So we're done with this one.
Good. So what is the complexity of your algorithm?
Right. So time complexity wise, we have a linear time taking method here. So this can be done in big of n time, and we have a loop which starts with n and down to 1. So this is going to be a linear loop again. But each pass of this loop needs to do these two things. And seeking to ith node takes, it's a linear with respect to I, but I starts with n and down to 1. So it is bounded by again big of n. This is a constant time taking method. So overall, the time complexity of this one would be, it belongs to big of n squared. That's how we put it. So this is time complexity. Coming down to space complexity, this doesn't require anything new. So I'm going to say space complexity requires big O of 1. That means it's just a constant extra space taking algorithm.
Okay. So good that you mentioned the space complexity as well. So if you look at the time complexity, it is an order of n square, which is quite expensive. Right? Can you think of a better method to solve the problem?
Yeah, I'm sure I can come up with a better method. Give me a minute.
Here is the discussed brute force solution. You can pause the video to take a detailed look into the solution.
I think I have a better method. So using stack, the idea of stack. So traverse the given list from the beginning, and then every time you see a new node, you insert into stack, and then print the stack in their popping order. You pop off, and then every time you print it. So that can print in reverse order. So every time, so when I'm traversing, I basically take the content of the node and then create a new node and insert at the head of the new list, which is going to be the stack essentially. So and then printing the stack is very trivial, which is as good as printing a linked list.
Okay, let's see the code.
Sure. So we have the same signature here. So for my new stack, key is going to be of the similar type, no star. So I'm just going to say stack itself. So this is null to start with. I'm assuming that null is a non-macro. While L is not null, so every time I'm going to insert a new node. So node is here. So I need a new node to be allocated. So I'm using malloc. And we should be checking for the null return of malloc in case malloc fails, but right now I'm skipping that. So node has a new node allocated, and node data is going to have data of n. Right. So when stack was pointing, wait a second. So because we are inserting at the head of the stack, so node dot next is going to be this stack. It's going to point to stack. And now stack I will repoint it to node. then L is going to point to the next node. And as long as L is not null, so we keep copying the contents of L and then insert into the stack. So this is basically, it created a new list in stack, which is a linked list essentially, and we're going to print it in a trivial way. So what we can do is while stack is not null, printf percentage %d, and now printing stack data. So stack is being pointed to the next one. So this whole thing can be a simple procedure to print a linked list, which is very trivial.
Okay, looks good. Where do we stand now in terms of the efficiency?
Right. So this while loop, in this one, everything is basically a constant time operation. So this while loop all takes linear time, and then there is another linear time taking while loop to print the whole list, another one. So overall, time complexity now has come down to big of n, and space-wise now we are basically creating a new list. We are creating n nodes essentially. So that's why the space complexity is going to be again big of n. So time-wise we have come down to big of n, which is the lower bound for this problem. What do I mean by lower bound is that is the minimum effort needed to solve this problem. So this is the best we can get for time. But space-wise we are now off. We had a big of 1, which is obviously the lower bound, but here it takes big of n space.
So the space is a bit of a concern here, right? Can you think of a better method?
Sure, let me try.
Here is the discussed solution with a new list. You can pause the video to take a detailed look into the solution.
Sure, I have a recursive solution for this one. I think that is better than the solution I gave. It's very elegant in a way, recursive solution. The idea is to print the rest of the list first with n-1 nodes and then print the current node.
Okay. Can you see the code?
Sure, it should not take much time. So if the base case would be if list is null, so there's nothing to do, so I'm just going to say return. Otherwise, I'm going to print the rest of the list in reverse order, so it's going to be the same recursive call. So I'll recursively call print reverse with next of L, which is going to be list having n-1 nodes. Now after this, I'm going to print the current node, which is the printf statement. I think that's all. It looks elegant, and coming down to the time requirement, because other than the recursive call, we take only constant time here, and recursion goes to a depth of n. So that's why it's going to take time complexity would be t of would be linear, right? Just like the earlier one. Space-wise, we don't take anything extra, so I'm going to say it takes constant space. I think this is the best we can get.
Do you really think the space complexity is order of 1?
Explicitly, I'm not using any extra space, but recursion always takes up some space, especially in stack. And in this one, the stack depth is of n, so we need a space for at the most n number of activation records.
Okay. So the space complexity boils down to big O of n.
That's right.
Right. So in that sense, it is not really an improvement over the previous solution, right?
Sure, I get it. So I think we cannot say that it's a big O of 1 solution. This is still big O of n. So
Cool.
it's not better than the previous one. It is as good as the previous one.
Right. So by the way, can you elaborate on the thought process by which you arrived at this recursive solution?
So the idea is very simple. It's actually straight from math induction because here we know how to handle the base case or the basis step, and then hypothesis is we assume that we can solve the problem for a size of n minus 1 in this case, and once that is solved, we are going to extend it to solve for the size of n, and that works elegantly here.
Good, that's interesting. But since we know that the time and space complexity are the same as the previous solution, do you think you can come up with a better method to improve upon the space complexity?
Sure.
Here is the discussed simple recursive solution. You can pause the video to take a detailed look into the solution.
I have another interesting solution, but that's going to modify the source. I can revert it back before returning, so that is acceptable.
Let's hear that.
Sure. So the idea is very simple. Given list, we're going to reverse it and then print in trivial order, and then reverse it back and return. So just a three-step method, which is kind of very simple.
Can you see the code?
Sure. So we have a list L here. So I'm going to say we can reverse this one. I'll just call reverse. This should be able to reverse the list, and I know this can be done in big of n time and big of one space. And so now the source list is modified. Now I'm going to print it. So we have seen already how to print a list trivially. So I'm going to say print and then L. So this is going to print linearly. This again takes big of n time and big of one space obviously. So I'm going to reverse again. So this is again another call for the same method here, which takes another big of n time and big of one space. Right. So because I reverted back to the original list, so whoever is the caller should not really worry about that.
Okay.
So overall time and space wise, I should be able to say now, time is big of n and space is big of 1, and both are lower bound. So this is the best we can get.
Looks perfect, but it's a little too simplistic.
Right.
In the sense that if you consider a multi-threaded environment, right? For example, if there are multiple threads, all of which are working on the same linked list, then this could result in trouble if you are going to modify the list window. Right? So more specifically to the point, I am looking for a solution wherein the time complexity is strictly less than quadratic and the space complexity is strictly less than linear.
Right. I get that. In every method, either time complexity is quadratic or space complexity is linear. So if I'm right, you are looking for something which is strictly lesser than big of n squared, and space requirement is strictly lesser than big of n.
That's correct.
Okay.
Here is the discussed solution with reversing the given list. You can pause the video to take a detailed look into the solution.
Okay, I have another interesting solution, which is kind of a combination of the stack idea we had, where we actually create a new stack, which takes big of n space, and another one is recursive idea, which has n nodes so that it goes to a depth of stack depth of n. If I combine both of them, I'm thinking of this idea. So where instead of having n nodes, I'm thinking of this as basically a list of square root of n blocks. So each of them is of size. This is a list of square root of n size, and then we have another list of square root of n size, right? So finally, I'm going to have the final list of square root of n, right? So this is list number 1, block number 1, block number 2, block number square root of n, right? So overall, we have n nodes. So because of that, so at the top level, my idea is recursive. So I'm going to print these blocks in reverse order. So that needs a stack depth of square root of n. And then for printing each block, I'm going to use that external stack idea, where I'm going to need again a square root of n space to create a stack and then print that in reverse order.
Okay.
So that's another big of n extra space.
Okay.
So both of them put together, it is just big of an extra space. Right? Time-wise, it is still linear. It's not that because both of them are linear, so it's just linear. Square root of n times square root of n is just n.
Okay. So the time complexity is going to be
Time complexity is going to be square root of n times square root of n,
okay.
which is just big of n.
So now we have reduced the time to big of n. The space has come down from n to square root of n.
That's right.
Is it right?
Yes.
Let's suppose that n is a very large number. Say for example that n is a trillion.
Right.
So square root of n in that case works out to be a million, right? Which is still a reasonably big number. Can you think of a solution where we can reduce the space complexity to log n instead of square root of n? So for example, if n is a trillion, log n works out to be around 40, right? Which is a significant improvement over a million.
Right.
So more specifically, what I want you to come up with is an algorithm that takes time proportional to n log n and space proportional to log n.
Here is the discussed solution with splitting the list into square root of n sublists. You can pause the video to take a detailed look into the solution.
I'm not sure about this method, but I'm just thinking through. So, because the space requirement you mentioned was big of log n. So, space requirement was big of log n. It's a very standard pattern when space requirement is log n. So, I'm thinking of a binary tree with say n nodes as leaves, and the height of the binary tree is going to be log n in that sense, if it is well balanced. So if you can do something like this, it can come down to the space requirement.
You seem to be on the right track. Please go on.
Okay, I'm basically going through a classic divide and conquer approach. In this case, I'm going to split the whole list into two parts and print the second part first and then the first part. Right. So if I use that method, I think we can get it. Let me try it on both. So this is the procedure you gave, but I'm thinking of basically a recursive way to divide and conquer where we need sublist to be printed, and sublist may not be null terminated. So I'm going to use one more end here. In this case, I'm going to say my recursive print. So print recursive I'm going to call. So this is going to have the starting node of the sublist, and end node in the beginning it's going to be L. So it's not the end node, it is the node after the last node.
Okay.
So
The
this
node
is
after the last node in your sublist.
right, node after the last node in my sublist. So for the whole list, null is the last the node after that.
Okay. Okay.
So this is the recursive call essentially. So I need to basically worry about a base case here. I don't want to call when L is null.
Okay.
So probably I'm going to just check for L being null. So if L is null, then I'm just going to return because there is nothing to do.
Right.
So otherwise, I'm going to use the recursive idea and just set recursive and L with null. So now this should do the job.
Okay.
Now let me elaborate how recursive function work. So I made sure L is never null. So the base case or the basis step for this one is going to be when there is only one node in the sublist. So that happens if next of begin is same as end, because end is basically the node after the last node in the sublist. If next is same as this end, there is only one node to print. So that is what we are going to do. So here printf the begin node essentially. So percentage d and begin data. And that's all we need to do here. So I'm going to return. Right, this is the basis or the terminal condition. Now we have to basically divide and print the second part first. Right. To do that, I need to basically find the beginning of the next sublist, which is the midpoint. So I'm going to say mid is that. So here again, so I'm going to say node star mid. I'm just assuming a procedure, a function here, which is seek mid when L is given. So it can be done in linear type, so where I can, even without knowing the length of the list.
What is L here?
Sorry, it's not L. It's
Begin.
It's begin and end. Okay. So even without knowing the length of the list, I should be able to find do that in linear time, linear to the size of the sublist.
Sure.
Right. So once we do this one, now mid is going to point to the beginning of the second part of the list, so which is end of the first list also. So I'm going to print the second part of the list first. So the recursive of mid is going to be the beginning of the second list and end remains as it. Okay. And after this, I'm going to recursively call begin with mid as the node or the pointer after the last node in the sublist. Okay. So this should do the job.
Cool. So now how do you compute the complexity of this solution?
Right. So this is just a wrapper function here. So there is nothing much to analyze in this one. But there is one recursive call, and if I look at the recursive call, let's see what do we do here. So this is just a base case. It takes constant time, and there is a linear time taking method here, which is linear to the size of the sublist. Okay. And there are two recursive calls of size roughly of each of them.
Right.
So I'm thinking of a recurrent solution here, because we call twice of the size of n by 2,
okay. 2
of t by n by 2, plus if n size is n, this is going to need a linear time to seek to the mid. Right. So another big O of n here, and the base case is just 1.
Okay. How do we solve this now?
Right. So yeah, we could use some methods of solving a occurrence like this. It's a very easy one.
Okay.
But yeah, this also looks like a very similar to the very popular recurrence used in merge sort, analysis of merge sort. So I kind of already know what is the answer for this one. It's going to be O of n log n.
Cool. So time complexity has come down to n log n.
Right. And space-wise, we don't take any extra space. We don't create, but we are going to basically the recursion is going to take up some space. And if I look at here, every time we are calling off of here, right. So the problem size is basically reduced by a factor of 2, and the depth of the stack will never be more than log n in that case. Okay. So it's all just a stack space requirement. So that's why it's going to be big O of log n.
Cool. So you got the time down to n log n, the space down to log n, which is what we expected you to do.
And I would also say that this is much better because log n is practically constant to us. As I mentioned, log of a trillion is only 40, which is practically constant to us. So time complexity is very near to just linear, and space complexity is very near to the O of 1.
Cool. That's great, Shana. It was great having you here. Nice to meet you.
Thank you.
Here is the discussed divide and conquer solution. You can pause the video to take a detailed look into the solution. Thank you for watching the video. Please leave a comment about it.